Okay. Here we go again. So, Math 20. Okay, Math 21B, Exam 1 review, bonus part A, first question. So, we need to state the null hypothesis, alternative hypothesis, and state what type of test this is. So before we actually even start with that, I want to ask you guys. Remember, there's 4 options here as to the free responses. It's either 1 population hypothesis test, 1 population confidence interval, 2 populations hypothesis test, or 2 populations confidence interval. Which one of those 4 is it?
I'm going to assume
1 population.
1 population.
1 population what? Hypothesis test. Good. This is a 1 population hypothesis test. Okay, this is a 1 population hypothesis test. So, when you use your formula sheet, recall Module 6 or Chapter 6, all of that is for 1 population. The first chunk is confidence intervals, so I don't want that. Just scroll down a bit more. There's the hypothesis testing formulas. Okay? Remember, you are able to make certain small edits, such that, for example, in the z-score, instead of writing p hat minus mu sub p, you could also write p hat minus p if you wanted to. I'm okay with that. Or if you wanted to make a note to yourself what the n stands for, if you want to say n is the sample size, I am okay with that. Remember, I will be checking your formula sheets to make sure there's not anything on there that's not supposed to be. For example, you cannot have any like written out examples. Okay, you can't have that. So yeah, so anyways, this is the portion of the formula sheet we will be utilizing. So let's state the null hypothesis, the alternative hypothesis, and what type of test this is. So the null hypothesis is always P equals, right? It always starts as P equals, and P equals what in this case?
25%.
25% or 0.25. Good, that's our baseline. So then the alternative is that P is what? Remember, there's always 3 options: greater than, less than, or not equal to. And in this case, it's what?
Less than.
Less than. Good, because it says right here, less than
Yo.
25%. So is this a left-tailed, right-tailed, or two-tailed test?
Left tail.
Left-tailed. Good. All right. Next, let's calculate the sample proportion. The sample proportion is denoted by p hat. So p hat equals, let's see here, from our sample, they surveyed 400 pet owners out of a random sample of 5,000. So we're going to set that up as 400 divided by 5,000. Oh, I dropped my pen, 1 second. Okay, so using your calculators, 400 divided by 5,000 is 0.08, or just 0.08, either way.
Sometimes working on the computer, what's that? If you don't put the 0, you put 0.08 and forget the 0, it'll come up.
You could do it either way on the exam, either 0 point or just the point. All right, next let's calculate the standard error. I don't know the standard error formula off the top of my head, so let's go to the formula sheet. And there it is, right in the middle. Standard error is equal to the square root of p times 1 minus p all over n. Okay? So the standard error equals the square root of p times 1 minus p all over n. Please be careful here. This is probably where I see students make the most common mistake. This formula says to use p, right? Not p hat. Not p hat. So what do we put in place of P here? Yeah, 0.25. It's what you stated up here at the start, 0.25. So please be careful. So it's the square root of 0.25 times 1 minus 0.25 all over the sample size. What was the sample size? 5,000. Okay. So using your calculators, 0.25 times 1 minus 0.25 all over 5,000, and the square root of that will give you 0.006. Rounding that to 3 decimal places. Next is calculate the z-score, the test statistic, which again, the formula is here. You can use that if you wanted to. But remember, some people like to write it as z equals p hat minus p all over the standard error. Really, it's up to you, your personal preference. So the z-score is equal to p hat, that is how I like it, p hat minus p all over the standard error. I guess I could have written that here. This is the standard error, where we know all 3 pieces of information here. We found p hat is 0.08. Minus p, we said, is 0.25. Over the standard error, we got that to be 0.006. Plugging that into your calculator, rounding it to 3 decimal places, is negative 28.333. Any questions so far? Okay. Next, find the p-value for your test statistic. Okay, so the p-value equals, we know we're going to be doing normal CDF. So tell me, is this problem going towards negative infinity or positive infinity?
Negative.
Negative. Good. And there's 2 ways to tell that. One way is because it's a left-tailed test, so it's going to the left forever, or negative infinity. The other way is your z-score. Since your z-score is negative, you should be going towards negative infinity. So we're going to start with the negative infinity because that's the smallest value, followed by the z-score, negative 28.333, and then 0 and 1, which, plugging that into your calculators, I believe that's 0, right? Yeah, it's 0. And 0 is the same thing as what percent? 0%. So either way. All right. Do we reject or fail to reject the null hypothesis? Do we support or not support the alternative, and why? I actually would rather start with the why portion. So since our p-value is 0%, what was our level significance? What did it say?
5.
5, yeah, at 5% level significance. So 0%, that's less than the level of significance, correct? Therefore, it is statistically significant. When it's statistically significant, we say that we reject the null and support the alternative hypotheses.
I was wondering, since like 0 isn't technically a number, I do understand it's lower than 5%, but isn't 0 technically nothing? It's just, 0. No matter what you do, 1 minus 0 is still 0. And, wouldn't it just be like you reject the null and alternative?
No. No, because as long, whatever your p-value is, as long as it's less than significance level, this is our conclusion. Yeah. Don't overthink if 0 is a number or not.
Then it's 0.01.
Because you could have gone technically this 0 could really be 0.000000000000002, and just your calculator doesn't go that far out on your digits. You know.
It's acceptable to write it just like that, p-value equals
Yes.
or not. That's
Yes.
why.
Yes. Yes. Yeah, exactly as I have it written here. All right, guys, one last part. Stating the conclusion. Remember, there's 3 pieces to the conclusion I want to see. First, restate the significance level. So, at the 5% significance level. And then state whether the sample data support or do not support the claim. In this case, the sample data support the claim, the claim being the alternative hypothesis. Support the claim that, and since we're supporting the alternative hypothesis, that's why we're supporting the claim. The claim is the alternative hypothesis. And then, so that's 1, restate the significance level. 2, state whether or not the sample data support the claim. And then 3, restate the claim. And then feel free to go back to the problem, because I already forgot what the claim was. And it says it here. The population proportion of pet owners in 2015 who believe vets charge an unreasonable amount for their services is less than 25%. That's the claim. So you could just recopy that word for word. So the population proportion of pet owners in 2015, the population proportion of pet owners in 2015 who believe vets charge an unreasonable amount for their services, who believe vets charge an unreasonable amount for their services, is less than 25%. This is a really good example, not just this part G, but the entire parts A through G, as to the level of work I expect to see on the exam for each step. Okay? I expect to see proper notation here. I expect to see how your p hat, right? It's not just enough to write 0.08. I want to see p hat. You need to specify that. I want to see your formulas and how you're setting it up. I want to see your substitutions here. I want to see, I know I can't see what you're typing into your calculator, so you need to write it out for me. Okay, you need to write it out for me what you're typing into your calculator. I expect these types of conclusions. Okay?
He has a question.
Oh, question.
Did you have a question? Or you-
No.
He did.
Oh, question.
So if it was the opposite, for G, we would just put everything, but instead we would just put does not support the claim that the population, and then the rest, right?
Yeah, so here, if this weren't true, like let's say instead of 0%, we got 10%, right? So if it was 10%, then you would put a slash through here, right? To say it's not less than the significance level, which means it's not statistically significant. We do not reject the null. We do not support the alternative. And then here, the only difference would be that at the 5% significance level, the sample data do not support the claim that, and all that stays the same. Not is the only difference. All right, guys, I'm going to stop. Oh, you can't see it again. Okay. Okay. So this is question 2 from the Math 21B Exam 1 Review Bonus Part A. In a random sample of 1,000 pet dog owners, 750 could correctly identify their dog's breed. Using the sample data, construct a 95% confidence interval estimate of the true proportion of pet dog owners who can correctly identify their dog's breed by answering the following questions. Part A, determine the sample proportion. All right, so that's going to be P hat equals, so let's see here. It was a random sample of 1,000 dogs, 750 could identify correctly. So that's 750 out of 1,000, which I believe is 0.75. Just double check.
Yeah.
Yep, 0.75. Okay. Part B. Are the conditions for approximate normality met? Well, oh wait, I should have backed up. From the start, I should have asked you, what type of question is this? 1 population hypothesis test, 1 population confidence interval, 2 population hypothesis test, or 2 population confidence interval?
1 population confidence interval.
Good. 1 population confidence interval. 1 population confidence interval.
That's gonna be part of the test?
No. No, I'm just having us practice this so that way you know how to reference your formula sheet.
So I was about to be like, oh.
All right, so we know we're going to be on module 6 looking at the confidence interval section, okay, which looks like this. And remember, take note that I added in a couple things in class. You didn't have to add them if you didn't want to. Really, it's up to you and your comfort level of what you want on your formula sheet. But what I included in class is allowed. So these are the formulas we will be utilizing. So when it's asking for part B, are the conditions for approximate normality met? It even says that here. It's at the very top. Conditions for approximate normality, right? N times P hat is greater than or equal to 10, and N times 1 minus P hat is greater than or equal to 10. So those are the 2 things we need to satisfy. Oops. Okay. So N times P hat and N times 1 minus P hat. So what was N? 1,000, good. P hat is 0.75, and that will be 75. And then 1,000 times 1 minus 0.75. I believe that's 25? Or no?
No, it's
250.
0.14.
Wait, let me double check. 1,000 times 1 minus 0.25. 750. I was way off. No,
You add it. Just 1 0.
I did that. Wait, I did that wrong in my calculator again. Sorry, guys.
75%.
1 minus 0.75. There we go. 250.
Yeah.
250.
And the first one is 750.
Is it really?
Yeah.
All right, guys, see. So for those of you who are watching the video later, I tried to do the math in my head, which I clearly cannot do. Always check with the calculator.
It's fine.
Okay. Any questions there, guys?
It just wasn't 100.
Yeah. I was like, something doesn't look right. I cannot trust my own math. Trust the calculator. All right. Are both of these greater than 10?
Yeah.
Yeah. So are the normality criteria set? Are the criteria blah blah blah? Are the conditions for approximate normality met?
Yes.
Yes. So this is for this type of question. This is what I expect to see. Okay. Okay. Part C. Calculate the estimated standard error. So if we come back to here, the estimated standard error formula is within the margin of error formula. It is the square root of P hat times 1 minus P hat all over N. And that's what I wrote out separately in class in case you wanted to have it designated and separated out. That is A-OK. So the estimated standard error is equal to the square root of P hat times 1 minus P hat all over N, which is the square root of, we have P hat. P hat is 0.75 times 1 minus 0.75 all over n, which we said the sample size was 1,000.
Yeah.
We don't put,
Question?
we don't put at the beginning 1.960?
Great question. That is the next part when we're finding the margin of error. But this isn't asking for the margin of error. It just wants the estimated standard error. And the estimated standard error is only this part. It's only the square root portion. Okay. And then so let me just flip back to the dot cam real quick. That's why I segmented it out here. So technically it's right here. So I mean, like if that's all you need, then that's all you need. But if you'd like, but that's part of the margin of error because again multiplied by the z sub c, the critical value. If you want to see it segmented out, just the square root portion is the estimated standard error.
0.14.
Is that what y'all got? 0.14? Okay. 0.
Point.
Oh, 0.014. Thank you. 0.014. That's rounding it to 3 decimal places. Next, we can find the margin of error, E, which is from the formula sheet, z sub c times the square root of p hat times 1 minus p hat all over n. Where z sub c comes from the chart, it comes from the table, and it's dependent upon your confidence level. So we are at a 95% confidence level. So go back to here. 95% has what z-score?
1.96.
Yeah, 1.960. So that's what you substitute in, 1.960. Then is the square root of p hat times 1 minus p hat all over n, but we already did that. We already did that in part C. So you could just substitute in the answer you got in the previous step, the 0.014. So 1.960 times 0.014. Rounding it to 3 decimal places, I got 0.027. Did I do that wrong? Or right?
Yeah, that's right.
You got that? Okay.
Yeah.
On the exam, do we have to write out the E equals CC square root, or can we just do 1.960 times,
I guess
0.014?
My recommendation is to always write out the formula because worst case scenario, let's say you did something wrong here, like in a previous step or just something. The more you write out to where the more I could see your thought process, the more opportunity for partial credit if something went wrong.
Professor,
Yes.
why did you cancel out the square root?
I didn't cancel out the square root, but notice here the square root of all of this, right? We already did. And we got this answer. So in place of this entire thing here, I don't want to have to recalculate this, right? I already did it. I already took the square root in the previous step. So instead of recalculating all of this, I'm just substituting this in place of the square root of everything here.
Because I did it the same as the formula and I got a different answer.
Well, if you had done it the same as the form, another way you could have done it, I mean, like if you wanted to, you could have also done 1.960 times the square root of p hat, which is 0.75 times 1 minus 0.75 all over 1,000, right? And then that might give you a slightly different answer because we had to round in the previous step.
Yeah.
Whereas here you wouldn't be rounding. So 1.960, if you did it this way, y equals 0.75 times 1 minus 0.75 all over 1,000. You get 0.0. Actually, once you round, you get 0.027 again.
Yeah, my bad. I did something wrong.
Okay, yeah, no worries. So either way, the intention of doing it, the intention of breaking it down into 2 steps for you, though, is to make your life easier.
Yeah.
That way you don't have to do this whole thing in your calculator. Instead, you're just doing 1.960 times what you got in your previous step. So it's meant to make your life easier, so that way you don't have to do this.
Now it makes my life harder.
Okay. So now we're going to write the 95% confidence interval in interval notation. So recall to do so, we need to do p hat minus e, and then separately p hat plus e, which we know what those values are. That's 0.75 minus e, which we just got to be 0.027, and then 0.75 plus e. So first in your calculators, subtract those values. I got 0.723. And then separately add those values. 0.75 plus 0.027. I got 0.777.
Do you mind if I take a photo of that?
Yeah, go for it.
Okay. All right.
All right. So now we can explain what this confidence interval means in the context of the problem. So let's see I already forgot. Let's reread it. What were we talking about here? Construct a 95% confidence interval estimate of the true proportion of pet dog owners who can correctly identify their dog's breed. Okay, so we are 95% confident that the true population proportion of dog owners who can correctly identify their dog's breed is between 72.3% and 77.7%. All right, that was the whole point of doing this. We don't know the population proportion. All we got was information for the sample proportion. But with that, we're able to conclude with 95% confidence the true proportion of pet dog owners who could correctly identify their dog's breed is somewhere between 72.3 and 77.7%. Any questions? And again, this if you get a one population confidence interval type question on the exam, this is the type of work I expect of you. Any questions?
In theory only, or in real life, or just?
In real life. In real life on Tuesday. Let me pause the record. Okay, this is the third and last question from Math 21B. Exam 1, review bonus part A. Gallup conducted a national poll asking, do you have a pet? Among women, 65% said yes. Among men, 74% said yes. You want to know if a similar result holds for the population of LBCC students. You claim that the proportion of women who have a pet is less than the proportion of men who have a pet at LBCC. You gather a random sample of 74 women and find 32 have a pet. You gather a random sample of 78 men and find 38 have a pet, and this should have said at LBCC. Use the sample data and steps below to test your claim at 5% significance level. All right, guys, so it's this one population hypotheses test, one population confidence interval, two population hypotheses test, or two population confidence interval.
Two population hypotheses.
Good. Two population hypotheses test. So from your formula sheet, from the formula sheet, that's going to be the module 7 side. Scroll down to where it says hypotheses testing And in class, I made 2 adjustments to it, which you were welcome to have copied if you wished to, but you did not have to. All right. I'm going to go ahead and label which group I want to be which. I'm going to call group 1 to be the women and group 2 to represent the men. Just because that was the order the information was given to me.
Is it gonna be labeled the test, or are we gonna do this? Are we just gonna?
Typically, you just follow the order that it says.
Okay.
So, like in this case, since it said,
Women first.
yeah, since it said women first, you claim that the proportion of women is less than men. So I just did women first, men second. So, what is the null and alternative hypothesis? So, for the null, now recall, whenever it comes to 2 populations, the null hypothesis is always P1 equals P2. Always. Oh, you can't see what I mean. Okay. Right? Because we know that the null is always an equal sign. And just this time, instead of your population being compared to a number, it's a population compared to another population. So P1 equals P2. And then for the alternative, P1, just like before, you have 3 options. Less than, greater than, or not equal to P2. And what is it in this case?
Less than.
Less than, because they said women less than men. So women less than men. You know, it didn't ask for it, but just for practice, is this left-tailed, right-tailed, or two-tailed?
Left-tailed.
Left-tailed. Okay. Part B. Calculate the difference in observed sample proportions. This is the same thing as asking for the sample difference, right? Sample proportions, we know that that's P1 and P2. And then what does the difference mean? Or what? To subtract, right? That's what that means. Calculating this difference in observed sample proportions or finding the sample difference. It's really just P1 minus P2. Oh, actually, I missed my hats. Sorry about that. Because it's sample proportions. So we need our hats. P1 hat minus P2 hat. Am I just given what those are?
No.
No. So I'm going to do that off to the side first. So P1 hat, that was for the women. So let's see here. For the women, out of 74 women, 32 have a pet. So 32 out of 74. 32 out of 74. Let's round to 3 decimal places. That's 0.432. And then similarly, calculate the sample proportion for the men. For the men, there were 78 men and 38 had a pet. So 38 out of 78. 38 out of 78 is 0.487. And then we're going to subtract those values. So 0.432 minus 0.487. 0.432 minus 0.487. That is negative 0.055.
I'm surprised.
Part C, calculate the pooled proportion. And there's a formula here for calculating the pooled proportion. That's the P bar. P bar equals x1 plus x2 over n1 plus n2. So P bar equals x1 plus x2 all over n1 plus n2, which in this case, it's just representing how many women and how many men have a pet out of how many women and how many men were sampled. So 32 women had a pet plus 38 men had a pet over 74 women were surveyed and 78 men were surveyed. That'll give us 70 over 152. or 0.461 once you round to 3 decimal places? Any questions there? All right, next, let's calculate the standard error, which from our formula sheet, the standard error is equal to the square root of p bar times 1 minus p bar over n sub 1 plus b p bar times 1 minus p bar all over n sub 2. So we have a formula for that. So the standard error is equal to the square root of p bar times 1 minus p bar n sub 1 plus p bar times 1 minus p bar n sub 2. Does this mean I can email everybody? I think so, yeah. Oh, I was right. Okay.
Professor, why do you call it P-bar?
Because of the little line that's above it. Looks like a bar. So that's 0.461 times 1 minus 0.461 all over 74 plus 0.461 times 1 minus 0.461 all over 78. Let me plug that into my calculator. All over 74 plus 0.461 times 1 minus 0.461 all over 78. I got 0.081. Anyone else get that? Yeah? Okay, cool. So take your time with your calculator there. Because the substituting part isn't too bad, and then the calculator, take your time for sure. Next, we find the z-score, and we have a formula for that. Remember, I did adjust it slightly when I wrote it down in class, so you could use the one that's provided here if you want. You'll get the same answer. I'm going to rewrite it the way you could also write it out. The z-score is equal to p1 hat minus p2 hat all over the standard error, which we already know what these values are. P1 hat minus P2 hat, we did above here. We got that to be negative 0.055. And then the estimated, and then the standard error, we just did in part D. We got 0.081. I'm getting negative 0.679.
Sorry, why did we get rid of the P1 minus P2?
So it's just these, so what I wrote here and what is provided here is actually equivalent. So this denominator is just the standard error, right? So I just rewrote it as the standard error. And then P1 minus P2, remember at the start, at the very stop, our null hypothesis, we said P1 equals P2, right? So if P1 equals P2, if they're the same, what happens when you subtract them? It's just zero.
Zero.
Right? It's zero. So then you don't need this because it just
So
becomes
in the
zero.
exam-
Oh,
I
so
don't
wait,
need
P1 and
P1 and
P2,
P2.
P1 and P2 is not,
Yeah, they gave us a
it's
P1
it's
and
not.
That was for the national,
Okay,
right?
that's
But
not
we
the-
aren't, the claim isn't with regards to the whole country. The claim was just with regards to LBCC students. We don't know P1 and P2 for LBCC students. So that's why on here, I rewrote the z-test statistic. You could leave it like this if you want, or you could rewrite it as follows. P1 hat minus P2 hat all over the standard
so
error.
I can automatically cancel out P1 minus P2.
Mm-hmm. Yep. Because it's just zero.
Okay.
Yeah, exactly.
Yeah, so this I would consider as a more simplified version. Technically they're the same. Technically you can use either one you want, but personally I think this is more simplified than this.
Now, me too.
Any other questions? Okay. We got 3 minutes. Find the p-value. All right, so p-value equals normal CDF. All right, so tell me, do I start with, or is this problem a negative infinity or a positive infinity problem?
Negative infinity.
Negative infinity, good, because it's a less than, it's left-tailed, and our z-score is negative. Good. Oops. So, negative 99999, negative 0.679, 0, and 1. Does anyone know what that is?
0.248? 0.249.
0.249?
Yeah, for 3 decimals.
Okay. Or, as a percentage, 24.9%.
Yeah.
All right, what was our level of significance? 5%. Okay, so our p-value is 24.9%. Is that less than or equal to our level of significance 5%?
No.
No. So I'm going to put a slash through that. That's not true. 24.9% is not less than 5%. Therefore, is it statistically significant?
No.
No, it is not statistically significant,
Hard work.
which means that we do not,
Not.
exactly, we do not reject the null. And do not support the alternative hypotheses. Which then we follow along with our overall conclusion. Remember, you restate your level of significance at the 5% level of significance. The sample data either support or do not support the claim. We're going to say the sample data do not support the claim. Right? That not keeps following. The sample data do not support the claim. That. And then you just rewrite what the claim was. If you forgot what it was, at this point, I often do, just go back to the problem. The claim was, let's see here, you claim that the proportion of women who have a pet is less than the proportion of men who have a pet at LBCC. The claim that the proportion of women who have a pet is less than the proportion of men who have a pet at LBCC. And that concludes it. All right, I'm going to stop recording to save back.